Okay, well, let's see. Now my video was interrupted when the battery died, so I'm going to have to start it over. I had to walk up and find my chalk. Okay, we're going to talk about fundamental triangles, and we're going to talk about rates of change. Now, a fundamental triangle is defined for 2 points in the coordinate plane. It actually could be defined for 2 points in three-dimensional space or higher dimensional space. This definition would be exactly the same, except it would be different. Okay, so here's a coordinate plane. Now here are 2 points. Let's see, we'll do a point here. We'll do a point here. Okay, so the fundamental triangle is a right triangle its hypotenuse is a line segment between the points. So very easy to write down the hypotenuse, or to sketch the hypotenuse. Okay? The legs are parallel to the coordinate axes. So what's that mean? Well, it means that this triangle has to have 2 legs. I could draw a right triangle. I'd have a leg going this way and come down here until I need a right angle to get back there. But this leg would not be parallel to either coordinate axis. So I can construct the triangle by starting at either point, but I'll start from the left, move to the right, mainly so I don't block the board moving from right to left. Or actually, I probably block it more moving from left to right. Okay, I'll start at the right. Okay, so I'm going to start at this point. Now I can draw a leg parallel to a coordinate axis from this point. Now these are the vertices. Clearly, if the line segment between the 2 points is the hypotenuse, this is a vertex and this is a vertex of the triangle. Okay, so if I start here, I could draw a leg parallel to the y-axis along this line. Turns out that that would go right through my writing here, so I'm not going to do that. But if I wanted to have one up here, I could do it. Okay? I'm going to start from here. Then I'll just draw, a line parallel to the y-axis. Okay. So the leg has to lie along this line, because that's the only way it could be parallel to the to the x-axis. I'm sorry, parallel to the x-axis from this point. Now, how far does it go? What direction does it go? Well, if I go out this way, I'm not going to get back here at a right angle to this line. I'm not going to get a right angle. I have to go over here. If I come over here to this point, then my second leg would have to go up here. That would not be at a right angle. If I don't go out far enough, I don't get a right angle here. If I go out too far, I exceed the right. Well, I go too far, I get an angle less than a right angle. So if I stop this leg here, I'm going to get an obtuse angle here. It's not going to be a right angle. We're not going to have a right triangle. If I extend the leg all the way out to here, then I'm going to have an acute angle here. It's not going to be a right angle. So I extend the leg to about here. Now we'll see a little more clearly exactly where that ought to stop, but that's probably pretty good. Then I have to do a leg through this point, okay? This vertex is done. We got the two sides of the triangle that meet at this vertex. We've got to have two sides that meet at this vertex. Now if I draw a horizontal side, try to draw a horizontal leg here, it's never going to meet this leg. We're not going to have a third vertex, we're not going to have a triangle. So I'm going to draw the leg along this badly drawn line, okay? And clearly then the leg has to go from here down to here. And it looks like I did go a little too far here, so I'll erase that a little bit, leave a smudge on the board. Okay, so there's my fundamental triangle. Now again, I could have drawn one up here. I'll just kind of sketch it out in a different color very lightly. You would have to come over to here. You would have to come up from here. So it'd be here. It'd also be a perfectly good fundamental triangle. We're not going to use that. We're going to use this one. Okay, now if we got the coordinates of these points, then we can do something with them, and something really important. Let's say this point is, let's say -6, 5. Smudge makes it worse, but hopefully you can read that. That's -6, 5. Okay, over here, let's say this is the point 5, -2. Now, we can determine the lengths of these two sides from these coordinates. Should be clear that this length is 11. From -6 over to the origin, then from 6 over to 5 is 11. And from 5 down to -2, we've got a distance of 5 and a distance of 2. The length of the leg is 7. Now on a fundamental triangle, we don't do lengths, we do displacements. And generally, what we're going to do is we're going to draw an arrow indicating our direction from this point to this point, or from this point to this point. Usually we go from left to right, but you can go from right to left, it would be fine. Okay, but I'm going to go from left to right here, drawing an arrow in this direction. So we think of moving from this point to this point. Now I'm going to draw corresponding arrows along these two legs that also get us from this point to this point. I'll draw an arrow here, draw an arrow here. Okay, so whether if we start at this point, it doesn't matter whether we go to this point directly by the hypotenuse or along the legs. I get from this point to this point. Don't want to run down the battery in that computer. Okay. So here we have it. Now we want to label the triangle with the displacement along each leg. So the displacement from here to here. Now displacement is not a distance, distance is part of it, but the displacement has a direction. And our displacement here is in the negative direction. So the negative direction from here to here we go, well, we're going from y coordinate of 5 down to y coordinate of 2. So the displacement is -5, and that's what we're going to label. Now the displacement from here to here is in the positive x direction. And we can see that it's 6 here and 5 here, so the displacement is 11. Okay, so there are displacements. Now, to get these displacements, we subtract where we end up with, well, we subtract where we start from where we end up. So the calculation for this -5, and it's important to know the calculation because sometimes we want to write these quantities in symbols. And we got to know how to calculate. If we got symbols here and symbols here, we got to know what the calculation is. Okay, the calculation is where we end up, which is at y equals -2, minus where we start, which is at 5. So we're subtracting where we start from where we end. -2 minus 5 equals -5. And here we're going from coordinate -6 to coordinate 5, and to do the calculation, we're going to do where we end minus where we start. 5 minus -6. Now we've labeled the sides and we've documented how we got those quantities. Okay, having done that, we could easily calculate the hypotenuse using the Pythagorean theorem. Just take this number and this number, square them both, add them, take the square root. We're not going to do that right now, but sometimes we want to do that. The main point I want to make here, which is related to rate of change, is we want to be able to calculate the slope. And that's easily done. Slope is rise divided by run. Now you might have been taught to memorize a formula, quantity y2 minus y1 over quantity x2 minus x1. It's exactly what you would get if this point was x1, y1, and this point is x2, y2. But that's a formula. You remember rise over run a lot easier than you remember formula, although if that formula's been drilled into you, you probably remember it pretty well. Okay? This is the reason behind the formula. And this is more important than the formula. Formula is something you use if you don't understand what you're doing. Slope is rise divided by run, and if you understand what you're doing, you don't need that formula, although there are things that the formula comes in very handy for. Okay, slope is rise divided by run, and of course we can identify this as the rise. And we can identify this as the run. So slope is rise over run, which equals -5 over 11. And we label that on the graph. So I'm going to label that on the hypotenuse. I'm going to put a -5 over 11 here. And I'm not going to just write this because now that looks like this is the distance. It's not the distance. Distance we would we could write here using the Pythagorean theorem. What is it? 121 and 25 is 146. It's the square root of 146. Okay, we could write that. Maybe I will here in a minute. So yeah, I'm going to write that. I'm going to write square root of 146. A number along a side or a leg represents a displacement or a length. Okay? On a hypotenuse, it's just a length because this is not along a coordinate axis. It doesn't have a displacement, it only has a length, hypotenuse. These are parallel to coordinate axes. They have displacements. Okay. Now, to distinguish a length like a square root of 146 from a displacement like, from a slope like -5/11, we're going to put a rectangular box around that slope. So when there's a rectangular box around a number or quantity, it represents a slope. Okay? Just a plain old number, square root of 146, represents not a slope or displacement, but a length in this case. Okay, and the square root of 146 is what? It's about pretty close to 11.5. interpolate between 121 and 169. It's 23 short of one, 25 over another. Say 11.5 is a pretty good estimate. And now that I think about it, 11.6 is a better one, but that's okay. Okay, so there's your fundamental triangle. That's all there is to it. Now that's related to the rate of change. So I'm going to give a definition of that. The rate of change of y with respect to x Okay, I'm being careless. And let's see, how am I going to fix that? We're going to obliterate that with Lysol foam and cleaner. And put the word average in. That's an average rate of change of y with respect to x. And I got the word is there. Don't want it. Need something first. With respect to x, in a set of coordinate axes, is the slope of the fundamental triangle between those points. Okay. So that's how we're going to define a rate of change, but we're going to explore what that definition is good for and why that definition is so profoundly important in mathematics. It's basically the foundation of calculus. We'll pick up on that in the next video.